We're going to connect these ideas with distance or displacement. So imagine a car is traveling at a constant velocity of 60 miles per hour along a straight highway over a 2-hour period. If we were to graph that, we could plot time and velocity, and it would be a constant 60. And we know that distance equals rate times time. If we made a rectangle here and we did the area of the rectangle, the length would be 2 and the height or width would be the velocity there, 60, and if we multiplied the 2 times the 60 we get 120, and if we did distance equals rate times time, since the velocity was constant, we would get the 120. So this leads us to the idea that if we could measure something, even if the velocity wasn't constant, if we could measure this over various time intervals, what if we knew the velocity at the car at 2 points and we find the distance traveled between those 2 points? So here we have 2 places, we clock it here, and then we go ahead and look at that as our little time interval, and we know distance equals velocity times time. And then we could look at all these little intervals and we could sum them up, and the idea is we would get these rectangles that could then approximate what this car was doing because it didn't have a constant velocity. The approximate distance would be the velocity times the little time interval, adding them up for each of these pieces. And so let's suppose that the velocity in meters per second of an object moving along a line is given by this function v equals t squared for t between 0 and 8. If we wanted to approximate the displacement of the object, we could divide this into time intervals, n subintervals of equal length, and approximate the velocity by a constant equal to the value of the velocity at the midpoint of the subinterval. So the same idea we've been doing as we were approximating the areas under curves. So if we did that for n equal 2, we could compute velocity times time in 2 different places and sum those up, and we would have an estimate. We would do better at 4, and of course if we did more rectangles we're doing better. If we did 64 rectangles, we've got a pretty good approximate. Here is a table looking at our different number of subintervals and what the length of each subinterval would be, and then an approximate for the displacement or distance, and it is going to be the area under the curve. So you can see that these appear to be approaching 170.6 something, and the idea is that the distance or displacement is an equivalent thing to the area under the curve.